All right. Hello. So this is section 14.7, part 2, which is global optimization. So we have two worksheet problems here. They are a bit longer than normal, but there are only two, so hopefully we can get through this relatively quickly. Okay. Find the absolute maxima minima of this function on this triangular plate. Okay. I always like to start these by just drawing a picture of what our region looks like. So here, let's see, I'm told that x equals 0. So when x is 0, it's a straight line upward like this. It's in purple here. Y equals 4, which is a horizontal line when y is equal to 4. And y equal to x. Okay, so that's that region there. And we want to find the, in the first quadrant. Okay. And we want to find the absolute maxima and minima of that function. Okay, so I sent out a sort of like procedure on how to do this. We need to identify all of the candidates for maxima and minima. So our candidates, as I said, are first critical points. So this is when the gradient of f is equal to 0. Let's see, the gradient of f is, this first component is going to be 2x minus y, and then the other two terms are constant, so they don't matter. And then negative x plus 2y. And so if this is equal to 0, we end up getting that x comma y has to be 0, 0. So I'm going to go ahead and highlight this. This is our first candidate. The second type of candidate is vertices. And so this is specifically where we have corners in our diagram here. So I see 3 corners, one here, and one here. This one here is at 0, 0. I think that's pretty clear visually. The second one, this line here is x equals 0, and this one here is y equals 4. And so their intersection is going to be where x equals 0 and y equals 4. Okay? And this last one, it's on the curve y equals 4, so we know that the y value has to be 4. And it's also on the curve y equals x, so we know that y has to equal x. So that point is 4, 4. Okay, so those are our 3 vertices, and we have to make sure that we include those as candidates also. So I already wrote 0, 0 earlier, so I'm not going to write it again. But we have 0, 4, and 4, 4. I'll make sure to highlight those to indicate that they are also candidates. Okay, the third type of candidate, which is the hardest, is what I call boundary critical points. And these are not critical points of f, but they are critical points of f when we plug in our boundary. And so what I mean by that, our 3 boundary components here, these 3 sort of edges, are x equals 0, y equals 4, and y equals x. So what we're going to do is we're going to plug each of those 3 equations into our original function. So we want f of x is 0. We want f when y is 4. And we want f when y is equal to x. So I'll find all 3 of those. The first one, when x is 0, that is y squared plus 1. The second one, when y is 4, that is x squared minus 4x plus 17. And the third one, when y is equal to x, I think you just end up getting x squared plus 1. Okay? So again, I'm just going to write over here the boundary conditions that I plugged in. All right, and then I find the I find the critical points of each of these. As a reminder, critical points are when your derivative of a single variable function. Critical points are when the derivative is equal to 0. So here I have df dy, which is 2y, has to be 0. and so y is 0. And since x was 0 over here on this boundary component, our critical point is 0, 0. We already labeled that as a candidate up here, and so I won't highlight that again, but that is what we would get. Also, I'll also write 0, 0 up here because we would get it, but I already labeled it. I already found it. Okay, our next boundary critical point, this is our boundary equation. We're going to set as a derivative equal to 0. So df dx is 2x minus 4. And so then x is equal to 2. And remember, on this boundary component, y was equal to 4. And so then our critical point is 2, 4. Okay, and then the last one, y is equal to x. I'm going to set df dx equal to 0. And so then 2x is equal to 0, which means that x is 0. And so then this boundary critical point, remember, on this boundary component, y was equal to x. X is 0, so y is also 0. Again, I already labeled 0, 0, so I won't highlight it again. But I will highlight that 2, 4 because I haven't done it yet. Okay, and that gives me all of my candidates. I found my critical points right here. I found my vertices right here. And I found my boundary critical points right here. And again, the reason I didn't highlight these 0, 0s, normally I would highlight them, but I already highlighted them up here. And so I don't need to do it again. All right, so now once we have our candidates, I just like to make a little table over here. So let's see, our candidates, I'm going to list them in the left column. So that is 0, 0, 0, 4, 4, 4, and 2, 4. And then we have to evaluate the value of our function at those points. So f of 0, 0 is going to be 1. F of 0, 4, I have to do this in my head, that's 17, I think. F of 4, 4 is 17, I think. Right? So when y is 4, or when y is equal to, yeah, 17. And then f of 2, 4 is 4 minus 8, which is negative 13, I think. All right. And so this is our absolute maximum. This is our absolute minimum. So your final answer would be, I guess, just max equals 17 and min equals 1. It did not ask you to find the points that the maxes and mins occur at. So this is a fine final answer. But if it asks also for the locations, you would have to give these numbers over here, these points. All right. So that's this problem. Hopefully we all understood that. I'll go ahead and move on to the next one. Move this up a bit to have more space. Number 2. Among all rectangular boxes of volume of 27 cubic centimeters, what are the dimensions of the box with the smallest surface area? And what is the smallest surface area? And then here, this part's really important. It makes the problem a lot easier. Assume this occurs at a local min of the surface area function. So basically, we're just trying to find local minima. But we already did that in the previous section, in the first part of 14.7. But we do need to set up this problem. Okay, so let's draw a rectangular box first. There is a siren outside of my apartment. And then that's our rectangular box. It has 3 dimensions, the length, the width, and the height. I will call those x, y, and z, just because I don't know which one's length and width. So my bad. All right, so we have the length, we have the 3 dimensions of our box. Remember, the volume is length times width times height, so that's x, y, z. Okay, and the problem says that the volume has to be 27, so I'll set x, y, z equal to 27. Okay, so that's my constraint. That is what you might call the region that I'm trying to optimize in. And then what are the dimensions of the box with the smallest surface area? So to get that, we need the surface area of the box. Surface area is 2xy plus 2yz plus 2xz, because there are two faces with area xy, these two. There are two faces with area xz, these two. And then there are two faces with area yz, which are these two. And I'm realizing at this point this doesn't look very coherent. But that's the surface area of a rectangular prism. Okay. And this is what we're trying to minimize. And so again, from the previous section, we can, if we're just trying to find local mins, we just set the gradient of our function equal to 0. So we just want local min. So we'll set the gradient of surface area equal to 0. I should say 0 vector. And so then the gradient of that is 2y plus 2z. 2x plus 2z and 2x plus 2y. And this is equal to 0, 0, 0. Something is not adding up because the solutions to this are just going to be 0. I'm sorry, normally this doesn't happen. What did I do wrong? I guess I didn't plug in my constraint. Yeah, that's really stupid. That's a stupid way to word this. Okay. So, okay, let's redo this. That's my bad. Okay, so it gives us a surface area and the volume functions. It does say assume that the smallest possible surface area occurs at the minimum, at a local minimum of the surface area function. It's leaving out that it wants us to plug in this constraint into the surface area function. And so I guess the reason that we want to do this is we saw that when I didn't plug in the constraint, we got that x, y, and z were all 0. Or we would have got that if I finished solving it. And that's a problem because if we plug that into here, that obviously won't satisfy the constraint. And so we need to find a solution so that x times y times z is actually equal to 27. And the only way to do that is to solve for z in this equation and then plug that into our surface area. This is basically the same thing as plugging in the boundary of your constraint, of your region into the function you're trying to optimize. Here, the boundary is just equal to the constraint, which is that x, y, z equals 27. So anyway, we need to solve for z. So we get that z equals 27 over xy. And then our surface area function is 2xy plus 54 over x plus 54 over y. Okay, and when they said assume this occurs at a local min of the surface area function, they meant this one. Or I guess I shouldn't box it. They meant this one, because that's the one where we plugged in the constraint, and so we know that x, y, and z, their product, the volume of the box is actually going to be 27. Okay, sorry about that. We can keep going now, though, because we need to find the gradient of the surface area function to find its local minimum. So that will be 2y minus 54 over x squared and 2x minus 54 over y squared. We're going to set this equal to 0. And so then I get two equations. The first one says that 2y is equal to 54 over x squared. And the second one says that 2x is equal to 54 over y squared. X and y can't be 0. If they were, the volume would be 0. And so I can go ahead and divide these two equations. When I divide them, I get that y over x is equal to y squared over x squared. Okay, and so then I cancel out a factor of these on both sides. I get that 1 is equal to y over x, and so then y is equal to x. All right, so I have that y is equal to x. Now I want to plug this back into my constraint equation to get z. Or actually, no, I want to plug this back into these equations to actually get y and x. So if y is equal to x, then I have 2x equals 54 over x squared. And so then x cubed is equal to 27. And so then x is equal to the cube root of 27, which is 3. And y is equal to x, so y also equals 3. All right? And now I need to find what z is, and that's when I go back to plug this into my constraint. I know that z is equal to 27 over xy. X is 3, y is 3, and so z is equal to 27 over 3 times 3, which is just 3. And so then our local minimum is when x, y, z equals 3, 3, 3. Okay, sorry about that problem. Main takeaway, when it said assume this occurs at a local min of the surface area function, they did want us to plug in the constraint first. I personally think that was a bit misleading, but we need to plug in the constraint to make sure that xyz is equal to 27. Hopefully the procedure of this problem makes sense. Anyway, that's both of these. If you have any questions about this, I think this problem is a lot more important that you understand. But if you have any questions about either of these, feel free to ask me. Otherwise, thank you for watching.